Hello students, in this session we are going to study some important numericals from the topic chemical equilibrium. Right? The most common problem for a student while solving chemical equilibrium numericals is when to take minus x, when to take minus ax in this way. See, this is the common error while doing numericals from chemical equilibrium. To avoid this situation, I will explain you three important points. Take it as a shortcuts, using which you can solve each and every question from chemical equilibrium. For example, we will start with the preparation of ammonia by Haber's process. N2 plus 3H2. Of course, all are gases which are at equilibrium with 2 moles of ammonia, which is also a gas. Here, as per the equation, what are the number of moles required? Number of moles required is 1:3. Number of moles of reactant that are required as per the equation are 1:3. Suppose in a question given to solve, if number of moles given are also 1:3. Then we have to proceed like out of 1 mole, some x moles of nitrogen will be contributed for the formation of ammonia. Even from hydrogen also, from every 1 mole, x mole will be utilized for hydrogen. As 3 moles are participating, 3 into 1 minus x. Right? 3 moles are participating, like this for 3 times it happens. Otherwise, if you are getting confused with this, as 1 mole of nitrogen needs 3 moles of hydrogen, out of 3 moles, 3x will be contributed for bonding. See, I am repeating. From nitrogen, how many moles are contributing for the formation of ammonia? X moles. Right? As 1 mole needs 3 moles, x mole needs 3x moles. Isn't it? That's why out of the 3 moles given in the question to solve, 3x moles will be contributed, 3 minus 3x will be left unreacted. So this is how we can solve. And 1 mole and 3 mole, totally 4 moles are giving how many moles? 2 moles. Likewise, x and 3x, so 4x moles will give 2x moles. 4x moles will give 2x moles. And the rest is the common procedure. Suppose if you are dealing with these are number of moles at equilibrium. Of course, these are number of moles at equilibrium. If you are dealing with the concentration, what's meant by concentration? Number of moles per unit volume. Suppose this whole reaction is taking place in a vessel of V liters, right? So concentration of nitrogen at equilibrium will be 1 minus x by V. Concentration of hydrogen at equilibrium will be 3 minus 3x by V, and concentration of ammonia at equilibrium will be 2x by V. Using which we can solve Kc. Kc is concentration of products by concentration of reactant. That is concentration of ammonia raised to the power of its coefficient over concentration of nitrogen into concentration of hydrogen to the power 3 coefficient. So what is concentration of ammonia here? 2x over V whole power 3 by concentration of nitrogen is 1 minus x by V into concentration of hydrogen is 3 minus 3x by V whole power 3. That's it. Rest of the procedure is quite common and simple also. So this is the first way of approaching a numerical. Once again I am repeating. Number of moles required is 1:3. If number of moles given is also same, then this is the way we have to solve. Let's come to the case 2. This is case 1. We have studied case 1. Let's come to the case 2. For the same reaction N2 plus 3H2, which is at equilibrium with 2NH3, number of moles required is again same, 1:3 only. And in the question, number of moles given for us to solve is 3:1, suppose. If the number of moles given for us to solve is 3:1, means number of moles given is different from number of moles required. Number of moles given is different from number of moles required. Then we have to follow limiting reagent. You know the meaning of limiting reagent, right? The one that gets completely consumed is said to be limiting reagent. Actually, 1 mole needs how many moles? 3 moles. Every 1 mole needs 3 moles. Then 3 moles needs actually how many moles? 9 moles. But here how many are present taken? Only 1 mole is taken. When 9 moles are required and 1 mole is taken, what does it mean? It is taken in less than the required quantity and it gets completely consumed. Such a substance which is taken in less than the required quantity is called as limiting reagent. So now, whenever number of moles given to solve is different from number of moles required as per the equation, then we have to start with the limiting reagent. So, out of 1 mole, composition corresponds to 3x moles of ammonia, because 3 moles of ammonia is reacting, no? Composition equivalent to 3x moles will be contributed for bonding. And every 3 moles needs 1 mole of nitrogen, means every 3x moles needs 1 mole of nitrogen. Every 3x moles of hydrogen needs 1 mole of nitrogen. That's why out of 3 moles of nitrogen given in the question, only 1x will be contributed, because 3 needs 1, so 3x needs 1x. Understood? That's why even though this is 3, very big number, out of 3 only the required x only will be contributed for bonding. Again, x and 3x will give 2x, because 1 and 3 are giving 2 moles, x and 3x will give 2x. Understood? So, the rest of the procedure is quite common. And then, next case is, suppose this is N2 plus 3H2 which are at equilibrium giving 2 moles of NH3. Case 3 it is. Number of moles required is 1 and 3. Number of moles required is 1 and 3. But if the number of moles given in the question is 2 and 6, if the number of moles given in the question is 2 and 6, means it's a multiple of 2. So like this, whenever given number of moles ratio is a multiple of required number of moles ratio, what we have to do? Solve it for number of moles required first. Solve it for number of moles required first. First we have to solve it for the required number of moles. What? 1 minus x, 3 minus 3x and 2x. Solve it for the required moles. 1 minus x, 3 minus 3x and 2x moles of ammonia. Then multiply the whole thing with this multiple. What is the multiple here? Number of moles given is 2 and 6, means it's a multiple of required ratio. What's the multiple? 2. It is 2 times of the required ratio. So with that 2, you multiply the whole thing. Whatever the multiple, suppose if it is given as 3 and 9 moles, it's a multiple of 3, yes or no? So that's what in such a case we have to multiply with the 3. In case if it is given as a 4 and 12 moles ratio, means it's a multiple of, given ratio is a multiple of 4, right? That's why we have to multiply this solved equation with the 4. Like this, we have to approach the 3 cases. Now, let us discuss this numerical from equilibrium. In the system CaF2 solid which is at equilibrium with the Ca plus 2 aqueous and F minus aqueous, increasing the concentration of Ca plus 2 4 times, the equilibrium concentration of F minus will be changed to, 1/2 of the initial value, twice the initial value, 1/4 of the initial value and thrice the initial value. Right? Now, which option? Let us solve. Here, as this is a solid, for this equilibrium reaction, equilibrium constant Kc can be given as concentration of Ca plus 2 aqueous into concentration of F minus square by, this stands for unity because it is a solid. For solids, concentration is taken as unity by 1. Now, what's the change they did? Concentration of Ca plus 2 is increased by 4 times. Concentration of Ca plus 2 is increased by 4 times. As equilibrium constant value should remain same, as equilibrium Kc value should remain same, whatever the change implied here, that should be nullified by the change in F minus concentration. As Kc value should be maintained constant, if you make some changes here, that will be nullified with some other change from F minus concentration. Understood? So, the product of 4 into change in F minus concentration, 4 into x square should be 1. Whatever the change we did, its opposite change should happen in case of F minus, so that Kc value will be retained back. Now Kc 4 into x square equal to 1, x square is 1 by 4, x is equals to 1 by 2. So concentration of F minus will be half of the initial value, will become half of the initial value. So it is 1/2 of the initial value. This is the answer for us. So this is how to solve a question from equilibrium. Now let us discuss one more numerical from equilibrium. In a reversible reaction, A giving rise to B, A at equilibrium with B, this is forward reaction whose rate constant is K1. This is backward reaction whose rate constant is K2. The initial concentrations of A and B are small a and small b in moles per liter, and the equilibrium concentrations of capital A and capital B are A minus x and B plus x respectively. Initial values are given, at equilibrium also given. Now express x, whatever the amount of reactant converted into product, express x, or it is also called as this amount, number of moles converted into products, express x in terms of K1, K2, A and B. Now which option is coming from this? Let us see. A at equilibrium with B. A at equilibrium with B. This is small a given, this is small b given initially. And at equilibrium, A minus x is left here, B plus x is formed here in moles per liter. Now, for this, Kc can be expressed as equilibrium concentration of B over equilibrium concentration of A. That is, B plus x by A minus x. B plus x by A minus x. Right? Now let us see. Here Kc is nothing but equilibrium rate constant of forward reaction by that of backward reaction, which is B plus x by A minus x. K1 into A minus x is equals to K2 into B plus x. On simplification, K1A minus K1x is equals to K2B plus K2x. Now by taking K1x that side, x into K1 plus K2 is equals to K1A minus K2B. So x is equals to K1A minus K2B over K1 plus K2. So which option is suitable for this? K1A minus K2B by K1 plus K2. So this is the answer for the given question. Let us see one more question of this type. The other question, 0.5 moles of H2 and 1 mole of HI were taken in a liter vessel. There is no I2 taken. In a liter vessel, hydrogen gas and hydrogen iodide gas were taken. No iodine is taken. No iodine, I2 is not taken. Are added to a liter vessel and allowed to reach equilibrium as per this equation. Equilibrium is established in this way. H2 plus I2 at equilibrium with 2HI. Now, if x is the equilibrium concentration of I2, at equilibrium concentration of I2 is given as x. Okay. In such a case, the correct expression, equilibrium constant expression for Kc will be, correct equilibrium constant for Kc will be, what's the answer? Right? Now let us see. Actually, everyone will start in this way. H2 plus I2 gives rise to 2HI. This is 0.5 mole, this is 1 mole, this is 0 mole. 0.5 minus x, 1 minus x, 2x. No, this is a wrong approach. You know why? Iodine is not given here. Iodine is not given. No I2 is given. Only 1 mole of HI is given. Only 1 mole of HI is given. So, how can, when iodine is not there, hydrogen will react with what? Hydrogen cannot react with anything, because that is the only reactant. How can it give HI when there is no iodine to react? So, what's the point to be noted? In this case, forward reaction is not possible. The reaction that is initiated is a backward reaction, means H2 plus I2 at equilibrium with the HI, 0.5 mole and 1 mole. as this is the reaction, out of 1 mole, number of moles corresponds to 2x. Number of moles corresponds to 2x of HI will be contributed to give H2 and I2. Backward reaction is initiated. 2 moles is giving 1 and 1. 2x will give x and 0.5 plus x. This is how the reaction will be initiated. And now equilibrium is established. Suppose equilibrium is established. Now, as it is in 1 liter, Kc expression can be given as 1 minus 2x Hi square. Concentration of Hi square means 1 minus 2x whole square by 0.5 plus x into x. Right? So, where is this expression? 1 minus 2x whole square. 1 minus 2x whole square by x into 0.5 plus x. So, for this question, valid answer is option 4. So, in this way, observe the question properly before solving. Such cases also will be specified. Now, this is another numerical from equilibrium. Active mass of 5.6 liters of oxygen at STP is. Active mass of 5.6 liters of oxygen at STP is. From this 5.6 we can understand that this numerical is based on old STP conditions. Already in the stoichiometric chapter we discussed old STP conditions, new STP conditions according to IUPAC both. Old STP molar volume is 22.4 liters, new STP IUPAC molar volume is 22.7 liters. Okay, this is according to old STP conditions. Now, active mass means, what's meant by active mass? Active mass is nothing but molar concentration. Active mass is nothing but molar concentration raised to the power of its coefficient. Now, we have to find active mass of oxygen means we have to find molar concentration of oxygen. How to find? Now let us see. We know that 22.4 liters oxygen at STP weighs 32 grams, that is for 1 mole, right? 32 grams means 1 mole of oxygen. Then this is for 1 mole, right? 1 mole of oxygen. Then 5.6 liters of oxygen at STP weighs 5.6 is 1 by 4 moles, 32 by 4, 8 grams, that is 1 by 4 moles of oxygen. So, we got number of moles of oxygen. What is molar concentration of oxygen? Active mass is nothing but molar concentration of oxygen, which is nothing but number of moles of oxygen per unit volume in liters. Right? So, it means number of moles of oxygen is 1 by 4 moles into what is the volume? 22.4 liters. Okay. So, 1 by 4 into 22.4, 0.25 by 22.4. So, we have to simplify this value. Right? Now, number of moles of oxygen by volume in liters. So, volume is not 22.4, it is given as 5.6 liters of oxygen. So, 1 by 4 into 1 by 5.6, that is 1 by 22.4. 1 by 22.4 means it is nothing but 0.25 by 5.6. These two are same, right? So, fourth option. So, this is how we can calculate active mass question, right? Let us do one more. So, let us solve this numerical. This is the equilibrium reaction given NH2COO NH4 at equilibrium with 2 moles of ammonia gas and CO2 gas. This is a solid, whereas the rest two are gases. Now, equilibrium pressure is 3 atmosphere for the above equilibrium. Then what will be its Kp? Equilibrium pressure constant is what? How do you calculate Kp equals to partial pressure of ammonia square into that of CO2 by partial pressure of this is unit 1. Now, we need to find out. There are two ways. One line method is there. As this is a solid, this is 2 moles and this is 1 mole. 2:1 ratio they are present, totally contributing 3 pressure, atmosphere, 3 atmosphere. So, ammonia is 2 atmosphere, CO2 is 1 atmosphere. So, Kp equals to 2 square into 1, 2 square into 1, that is 4. This is one way, simple way, 4 atmosphere. Option A will be the answer. Now, if you want a systematic procedure, see, it is NH2COO NH4 at equilibrium with 2 moles of NH3 plus CO2. Then this is 1, 0, 0 initially. At equilibrium 1 minus x, 2x and x. So as this is a solid, its number of moles won't contribute to the Kp. So now mole fraction of ammonia can be given as total moles 2 out of, this is 2x plus x, total moles are 3x. So mole fraction of ammonia is number of moles of ammonia out of total moles, it is 2 by 3. Mole fraction of CO2 will be number of moles of CO2 out of total moles 3x, that is 1 by 3. Now Kp equals to mole fraction of ammonia into total pressure whole square into mole fraction of CO2 into total pressure. Now what is mole fraction of ammonia? It is 2 by 3 into 3 square, it is 1 by 3 into 3. 3 are cancelled, so it is 2 square into 1, it is 4. So this is systematic procedure. See, it had taken more than 2 minutes. Instead, if you follow the shortcut, what is that? See, what's the shortcut? As this is 2:1 moles ratio, these are the only gases totally contributing 3 atmosphere total pressure, means partial pressure of ammonia is 2, CO2 is 1. Then Kp can be simply given as partial pressure of ammonia square into partial pressure of CO2 4. One line. In maximum 20 seconds we can solve this, right? This is how we can answer in simple step shortcut and in systematic procedure. Let us see one more question. So this is our next model question. A plus B is at equilibrium with C plus D. There is an equilibrium between reactant capital A and capital B and products capital C and capital D. If initially the concentration of A and B are both equal, but at equilibrium concentration of D is twice that of A, means what? Equilibrium concentration of D is twice that of A. Then what will be the Kc of the reaction? For example, A plus B is given at equilibrium with C plus D. Initially this is 1 mole, 0 and 0. Now these are the number of moles initial. Number of moles at equilibrium will be 1 minus x, 1 minus x, x and x. This is the equilibrium concentration of D and this is that of capital B and capital B. Now what's the line given? Equilibrium concentration of D is twice that of A, means x is 2 times of 1 minus x. X is equals to 2 minus 2x, x equals to 2 by 3. X is given as 2 by 3, right? Now this x we have to substitute in this numerical. What is that? 1 minus 2 by 3, 1 minus 2 by 3, 2 by 3 and 2 by 3. Now we got the concentration, equilibrium concentration of A, B, C and D in particular, right? Then Kc can be calculated as equilibrium concentration of C into D by A into B, that is Kc equals to 2 by 3 into 2 by 3 by 1 by 3 into 1 by 3, it is 4. Kc is equals to 4. So this is the value. Suppose if the options are given as first option is given as 1, second option is given as 2, third option is given as 3 and fourth option is given as 4. Then what's the answer? Kc value is set to be 4. This is the present numerical. Let us discuss